All right, the second part of this section is properties of limits and just kind of some basic algebraic limit evaluation. So the properties of limits, they're all kind of written out here. We'll do this occasionally, just give you throw a bunch of properties at you. So the limit as x goes to c equals L and of f, and limit as x goes to c of g equals m, then basically, like these all kind of work the way you would think they would. If you add or subtract the functions and you take the limit of them, you add or subtract their limits. If you multiply the functions, you multiply the limits. If you take the limit of the quotient, you divide the limits. If you have a constant, this k is a constant. If you have a constant times your function, you're going to take the constant times the limit. And if you have a function to a power, you can take the limit to a power. The only one that doesn't quite work the same way is a composition of functions. Typically for a composition of functions, I'll write this one out, but this is not always the case. It depends on the continuity of the functions. So I hesitate to even write this, but the composition of functions typically, depending on the continuity, so this depends on continuity of the functions, and we'll talk about continuity in a little bit. You take the limit of the inside and you plug it into the outside. That is not always the case because of continuity. So if your function has discontinuities, if you have to pick up your pencil to draw the function, then this may not work. All right, you may have to actually take the limit of the outside part. Okay, but this is typically what happens if your functions are continuous. Basically, all this is to say that if you have the limit of a function, you can just plug in the number if you get an answer. If you don't get an answer, then you have to do other stuff, which we'll talk about later. But for now, you know, this right here without the x squared, this is a limit of a difference of functions. One function is 2, the other is x. The limit of the 2 is 2. The limit of x, if you plug in the 3, is 3. So you can just do 2 minus 3, obviously. I mean, it's what you would expect to do, common sense. So if you should always start by plugging in 3, because if your function is able to be evaluated at 3, if your function is continuous and everything, then that's your limit. All right, so algebraically, limits are not typically that difficult if they give you a number back. If they don't give you a number back, that's a different story. So we plug in 3 for x, and 3 squared is 9, 2 minus 3 is negative 1, and we get negative 9. All right, you're going to try with this one in the Nearpod, so figure out what that answer is. Okay, so then we have a piecewise function. So piecewise functions are where this gets exciting. This first one is not very exciting. So find the limit as x goes to 0. So for piecewise functions, remember where you evaluate them, if we were just finding f of 0, you'd look at your inequalities and say, oh, 0 fits into this one, and then you'd plug 0 into your function. It's the same thing for a limit. The only difference is if the number that your limit is going to is one of these breaks in the piecewise function, then you have to do something a little different. And I've actually written out the steps for you on this first one. So the limit as x goes to 0. 0 fits in this middle inequality. So our f of x would actually be 5. And there's no x to plug 0 into. So this is just equal to 5. All right, if 0 had happened to fit into the top one, we'd plug in 0 for x and get negative 2. All right, now if you're taking, like oops, this should be a negative. If you say this was just the problem, limit as x goes to negative 1, that's not a 7, now it looks like a 7. Limit as x goes to negative 1 of f of x. All right, negative 1 is where this function switches between x squared minus 2 and 5. All right, so when that happens, you have to look at the limit from the right and the limit from the left. All right, you cannot just take this limit. Okay, you have to look at the two sides. So limit as x goes to negative 1, I don't know why I always write the plus first. You look at your inequalities. Which one is x greater than 1? Because the plus means bigger than 1. The middle one. So this is going to be taking the limit as x goes to negative 1 of, with a little plus, of 5. All right, and that equals 5. And then the limit as x goes to negative 1 with the little minus All right, so then the minus is less than 1. So we're looking at where is x less than 1? X squared minus 2. And we plug negative 1 into that. Negative 1 squared is 1, minus 2 is negative 1. All right, so then our total limit, remember when we were doing the tables or when we were doing the graphs, these two had to agree. These two, 5 and negative 1, obviously are not the same, so this limit does not exist. All right, you're going to do this exact same thing with x equals, or x going to 5. So I did not write out the two sides of the limit, but you're going to do them to figure out what this limit is. All right, and then you're going to have your answer in your pod. Let's take a look at this one, and then there's just have a couple of extra notes down there. So let f of x equals this type of piecewise function. So this is different than the one before. And the one before had a bunch of inequalities, less than, greater than, blah, blah, blah. This one is different. This one, your function is this for x not equal to 2. So for all x except for 2, your function is this. When x equals 2, it's 5. All right, so we want the limit as x goes to 2 of f of x. Now this is where, again, I say this all the time. The limit is what's happening around the point, not at the point. So if we wanted to find f of 2, it would be 5, okay? It would be this, okay? This is what you would use for f of 2. If we want to find the limit, we are using this piece of the function because the limit does not care what's happening at the point, it's what's happening around the point. So we don't have to do the two sides of 2 because our function is the same on either side. But we don't want to use x equals 2. We want to use what it is around 2. So we take the limit as x goes to 2 of 3x minus 2 over x. And if we plug 2 into that, that's 6 minus 2 over 2, which is 4 over 2, which is 2. Okay, so our limit is 2, whereas f of 2 is 5. Okay, so that's a big, important deal. One of the things that I'm going to try to pound into your head over this year is that the absolute value is actually a piecewise function. Right, absolute value, what we know of it, everybody says it makes everything positive. It's the distance from 0. So absolute value is actually a piecewise function. It's x when x is greater than 0. The equal to can be on either one of these. I always put it on the greater than. So it's x when x is greater than or equal to 0. It's negative x when x is less than 0. Because if x is less than 0, x is negative. And a negative negative makes it positive. All right, so that is a piecewise function. So if you have something other than x inside of the absolute value, how do you write it as a piecewise function? Well, this is no longer 0. This number is the 0 of the inside. It's what number makes the inside 0. Basically, the x-coordinate, the vertex of your v. Okay, if you learned that in Algebra 1, Algebra 2, I don't know. But it's what makes the inside 0, basically. So negative 4 makes it 0. So here's negative 4. Greater than, less than. I always put the equal to on the greater than, but you could put it on the less than if you wanted to. The greater than always gets the original thing without the absolute value, and then the less than always gets a negative. And you can distribute the negative if you want, but you're always going to have a negative there. So absolute value is a piecewise function. Very important when you're taking your limits and when we go further on in calculus.